Navigation is the art and science of conducting a vehicle safely to its destination, be it ship, aircraft, or land-based vehicle. Men have practiced this ancient art for thousands of years, using the stars to guide them. Today, however, the science of navigation grows more complex as the need for precise navigation increases. Our ships must calculate their positions and courses precisely as they travel over long ocean distances. Ground forces must be able to pinpoint their exact locations under all conditions. Today's high-speed aircraft, traveling in our increasingly crowded skies, must know exactly where they are at all times. The Department of Defense has a vital interest in precise navigation and is constantly seeking new approaches to precision navigation. One of the most promising is a space-based radio navigation system using several satellites. The Air Force Systems Command's Space and Missile Systems Organization, SAMSO, is responsible for developing the system. The Defense Navigation Satellite Development Program has been established within SAMSO to manage the planning of the system. SAMSO personnel are conducting extensive tests to prove the feasibility of the navigation satellite concept. A series of tests at White Sands Missile Range, New Mexico, provided important data on the effectiveness of this emerging concept. These experiments used ground-based transmitters instead of satellite-mounted transmitters. A simple inversion of conditions which provided a low-cost testing method. A specially instrumented aircraft simply flew over the transmitters, gathering data instead of under them, as would be the case for a space-based system. One segment of testing proved the area navigation capability of the system. 4 ground-based transmitters sent signals which were picked up by a mobile calibration station. This equipment provided the necessary synchronization to make precise calculations. A C-135 aircraft with radio receivers flew over the test area, also receiving the signals. This data was used to calculate an estimate of the plane's position and course. A second phase of the testing used 3 ground-based transmitters and a 4th suspended from a tethered balloon. The airborne balloon transmitter gave the test configuration a 3-dimensional quality, realistically simulating the satellite configuration in space. This testing verified the instrument landing application of a navigation satellite system. Once again, the mobile calibration station received the signals and recorded them for later use in data analysis. The C-135 flew a carefully controlled path along a 2.5-degree glide slope, simulating the conditions of an instrument landing. The pilot was assisted by an optical landing aid that gave him a reference point on the relatively featureless White Sands Desert and that helped him maintain the precise glide slope. In addition, visual sightings through a theodolite provided guidance information that was radioed to the pilot. During each pass, electronic equipment in the plane received signals from the transmitters and recorded them on magnetic tape. This data, combined with information from the calibration station about the slightly different transmission times of the 4 transmitters, was converted into a determination of the plane's trajectory. During this phase of testing, the plane made touch-and-go landings. The time when the wheels first touched the ground was recorded by equipment in the plane. The point of contact with the runway was later accurately surveyed. These measurements gave the experimenters known points in space and time against which to compare the system's determination of the aircraft's location. While receivers and recorders on the plane collected data on the system's performance, White Sands instrumentation also recorded the plane's path, providing data for a precise determination of its trajectory at each moment of the flight. This conventional trajectory data, derived from the White Sands tracking equipment, was later compared with the trajectory data from the satellite system's receivers. This and other related experiments indicate that a navigation satellite system can provide an accurate determination of an aircraft's position at each moment of the flight. Future Air Force effort will be directed toward the evaluation of those conditions which cannot be tested on the ground. These areas of research include the development and test of a variety of receiver techniques to meet performance requirements, the determination of computer requirements for representative users and missions, radio wave propagation corrections for ionospheric and tropospheric effects, and the perfection of methods for accurately determining satellite orbits. The Defense Navigation Satellite Development Program will launch a satellite system to continue research and development of these factors in a space environment. The technology produced by this program will lead the way to future systems that will satisfy increasing Defense Department needs for precise navigation. From the early tests at White Sands through the launch of an initial demonstration system, the ultimate goal of this effort is a global navigation system that will serve the defense needs of the 1980s. Defense Department effort will culminate in a uniform and extremely accurate satellite system, satisfying a broad range of civilian and military requirements.